the regular section, but this is something we've already done, so it's not a big deal. Plus, the actual algorithms are quite easy here, so I'll spend some time with that. And there's something going on Sunday, some of you might have heard. This is optional. So there's no impact to grades, homeworks, and exams. You can see these lectures either live, be here in this room, 11 a.m. It will be here in this room. Or you can skip it. Or you can watch the video later. It's up to you. That's going to be number theory, part 2. The notes are already online on the schedule website. This is the Rsa Cryptosystem. So if you want to see how a real cryptography works, what's the mathematics behind the real cryptography, that's not the linear ciphers we did so far. It's Rsa, that's quite used in practice. Of course, in cryptography, there's a lot of implementation details and like computer science details. What we're going to talk Sunday about is the math behind it, what makes it work, and why is it hard to break. So all the breakups and hacking that you've heard of, like NSA and you know, most recently, there were all kinds of stories how the people hacked in. None of these hacks were due to breaking the math of RSA. They're all due to engineering implementations or watching over shoulder password or listening in. So far, nobody figured out the way to break the math. Okay, so that would be something that we used to teach in this course, but due to the reshuffling, we thought maybe take it out and instead do more induction and graphs, which is what we have. I think that's a good thing, but for the other sections, we'll have this RSA as an optional lecture with no assignment of it and no requirement on notes. That being said, where are we? Let's recap here the modulo arithmetic so far. A is NQ plus R, or BQ plus R, is the integer division of A to B. Q is the quotient, R is the remainder. The remainder is in ZB, which is 0, 1, 2, up to B minus 1. We say A is R modulo B, or A modulo B is R. That means the remainder, when you divide A by B, integer division is R. The first theorem is that if A1 equals A2 modulo B, that's if and only if B divides the difference, A1 minus A2. We already talked about this. We even tried the proof a little bit. So this is theorem 1 here. It says, you know, if A1 is BQ1 plus R, and A2 is BQ2 plus R, they have to have the same remainder, so it's the same R. Well, that's the same as saying A1 minus A2 is B times Q1 minus Q2. This is not a formal proof, just for you to see where it's coming from. If they have the same remainder, when I take the difference, I get B times the difference in the quotients. So now, obviously, that's a multiple of B right here. And the other way, if A1 minus A2 is a multiple of B, when I add the reminders, I should get the same reminder. So you should complete this proof as an exercise. It's very easy. It's also on the notes. The notes I'm referring to is number theory part 1, the one that's required for quizzes, exams, and so on and so forth. The other theorem we have here is the factorization into primes is unique. We talked about this. So any number A is some prime at some power. different power. And another theorem. Those are very simple things that can be proved immediately. If a P is prime and divides a product, it must divide one of the factors. So this is very easy to see from the factorization. If prime P is a prime factor in the product A times B, the only way that can happen if P is a prime factor of A or a prime factor of B, because the primes in A times B come from the primes in A and the primes in B. So if it wouldn't be in either A or B, it wouldn't be there. And P being prime, it has to be one of the primes in the product AB. It's not like a combination of primes. It has to be prime itself. Again, these are very simple proofs. In fact, there is no actual proof sequencing here, reasoning. All you have to do is to understand how factorization works. If you understand how factorization works, the proof is just that, understanding factorization. But you gotta spend a little bit of time. If you're not familiar with this kind of thinking, you'll get in trouble during the final exam. What do you mean P divides a product, divides one of the factors? Try an example, right? P, a prime number 11, if 11 divides, I don't know, 143, which is, let's say 286, which 286 is, I believe, 22 times 13, maybe? 11 being prime, it has to divide one of the two factors in here. So you should try out these things and see why is it true for a prime, but it's not necessarily true if P is not prime. Like if P divides A and B and P is not prime, A times B, it's not necessary that P divides one of them. It only works that way if P is prime. Again, this is not a reasoning challenge. It's just a matter of you trying out those things with P prime, with P non-prime, and see why is that? How come it happened? Right? So for 11 here, it works. But if you put some number here like 10 or 20, maybe it doesn't work. We talked about GCD. That was the common primes at smallest power. Lowest power. Let's be more clear. So for example, if 60 is 2 times 3 times 5, and 50 is 2 times 5 squared, then GCD of 60 and 50 is 2, because this is the smallest power is 1 here, times 1, 5. Again, 5 is common, but the lowest exponent is the 1. And this actually works for more than 2 numbers. I could have here 40, which is 2 to the third times 5. Let's actually make it 2 to 8, 2 to the fifth, fourth times 5. If I add here 80, I apply the same algorithm. What is common to all three? There's only 1 2 that's in common and 1 5. I get the same GCD. So this principle, take the common factors at the lowest exponents, gives the GCD a bunch of numbers. LCM is a very similar thing. I won't repeat that. It's in the notes. Here's a theorem that we didn't say that's the same like those, not intellectually challenging once you understand what it's saying. If some factor divides A and divides B, 2 numbers, then it must divide the GCD. Let's write GCD with capitals. So any factor, not just primes, any factor that's a factor between 2 numbers, it has to be a factor of their GCD. So this theorem, it's equally easy with the rest by the prime factorization. This factor f here to divide both of them, it has to be composed of primes numbers that are both in A and B. So if F is some P1 at E1, P2, E2, Pk, Ek, what does it mean F divides A? It means all these primes have to be in A factorization, right? So it means all Pi at Ei are part of A factorization. Similarly, if F divides B, that means the same primes, all these Pi at Ei, those are the primes in this factor F, are part of B factorization. But what happens to those prime numbers that are both parts of A factorization and part of B factorization? If they are part of both of them, they will be part of the GCD, right? By definition, GCD includes all the primes at the smallest exponent. So because they're part of both, that means all those Pi at Ei's are part of GCD of AB, and that's where the theorem comes from. Now all the primes of F are part of the GCD, therefore F is dividing the GCD. All these theorems are not so much, again, a reasoning sequence as much as they are, you understand how prime factorization works. And of course, primes cannot be substituted with one another. If you want to have a 5 in here, the only way to get at is to have a 5. You can't substitute a 5 with different prime numbers and get the same result. If you want to have two 5s, you need to have a 5 squared or more than squared. That's the only way. You can't substitute two 5s with, say, 2, 3s, and 7s, and 11s. In a prime factorization, the only way to get 5 at the power 2 is to have two 5s in there. Who's with me so far? I'm insisting on the fact that you should spend some time studying not so much the reasoning like we had in induction or on this other proof binomial theorems, but rather what are those theorems actually mean? Take some examples. What does this mean? This means, for example, if I take A equals 60 and B equals 100, their GCD is what?
20.
How much is the GCD between them? 20? What this theorem is saying is any factor that divides both A and B, divides B, will have to divide 20. So for example, F could be 10, because 10 divides both of them. Right? Or F could be 5. 5 divides both of them. Any factor that divides 60 and 100 has got to be a divisor for 20. So I think it's important, again, to play with some examples in these theorems. Not so much to understand, there is no real proof here, it's just understanding the setup, how those primes number work in the composition. So what did we do all this so far? Now I'm back at where we left on Tuesday, which is the Euclid theorem. We did two versions of Euclid. Remember, we did the basic one that actually Euclid stated. That was saying you want the GCD of AB, that's the same as GCD of, what did Euclid say? A minus B and B. And somebody later on said, yeah, that's okay, it works, but I can speed it up by subtracting all the b's I can subtract at once. Remember the example we had on the board that you subtract that b, that's 6, like 5 times. Somebody said, why not just say fast version? If A is BQ plus R, I can take all the b's, Q of them, out at once. And then the theorem becomes GCD of AB is the same as GCD of B and I. Point being, if I subtract B enough times of A, I'm going to end up with R, right? If I repeatedly do this, in fact, how many times do I need to apply the subtraction here to get to R? A minus 1B, A minus 2 B's, 3 B's, 4 B's. How many B's do I need to subtract until I get to B and R? Q of them, right? So this step is saying, do the first step few times in one shot. So that's what we want to prove. We'll do this one here, because it's the fast one. It's what everybody uses in practice. It's what we did at recitation, right? We didn't do this at recitation. We jumped directly into from AB to BR, right? So what do we prove here? We want to prove that those GCDs are the same. I'm going to say proof. D is the GCD of A and B. So I'm looking at this equation, R equal I minus BQ, right? D is a GCD, so D must divide A and D must divide B, because clearly the GCD divides the two numbers. Now, I'm looking at this equation. This is a multiple of D, and this is a multiple of D. From here, D must divide R. Again, D divides A, D divides B, therefore BQ. So divides this and this. That means A is a multiple of D, BQ is a multiple of D. When I make the difference, I have to get a multiple of D. Every time I take a difference or a sum of a multiple of anything, I'm ending up with a multiple of that, right? We all understand that. So D divides R. Let's take now the G, the other GCD, GCD of B and R. Now I have here this G must divide D. The G must divide R because it's their GCD, it's a factor. I'm looking at this equation a little different this time. I'm saying A equal BQ plus R. And now I have G divides the B, therefore this part. G divides the R, this part. That means G gonna have to divide the sum. It's backwards. It's the same reasoning here, just backward. This one was A and B, therefore R. This one is B and R, therefore G must divide A, because when I take multiple of G, when I make the sum, I get the multiple of G. Hands up, who's with me so far? Good. Now I'm looking at this D and I'm saying D divides R, but I know D divides B. And I apply this theorem right here. I'm saying if a number, any number divides two other numbers, it must divide their GCD. So let's call this theorem 4. And say from theorem 4, D must divide the GCD of B and R. Again, it divides both, so it must divide their GCD. But who's the GCD of B and R?
G.
D must divide G. Same thing in here. G divides B, that's given from before. So because it divides two numbers, it must divide the same theorem 4. It must divide the GCD. I said capital GCD, right? Of A and B. But who's the GCD of A and B?
D.
So G divides D. The only way two numbers divide each other is if they're equal. I'm assuming they're on the positive side. I'm not counting on negative numbers here. When I talk about GCD in this context, I don't mean the negative numbers. So from here, I conclude D equal G, which is what I wanted to do, right? That was my purpose from the beginning, to prove that those two GCDs are the same. Now, this is a very formal proof. too formal for what we need. Somebody inevitably after this proof comes to me and say, wait a minute, I'm just a computer scientist, okay? I don't want to be a mathematician. If I wanted to be a mathematician, I would have gone to the math department, right? So I didn't. That's why I don't want to see formal proofs. Okay, you're right. Do I require you to know this kind of formalism in an exam? No. Do I expect you to know only, there's quite a few of you who are double majors with math. I get to know you by now. These people obsessed with math will certainly be interested in this. You have to understand the intuition here. That's required. You don't have to know how to do this formalism, but the intuition you should understand. In a linear equation like this, the GCD propagates. The GCD between A and B is the same as the GCD between B and R. It propagates both ways because this is a linear form. Either this way, which is a plus, or this way, same equation with a minus. GCD will propagate. That's the principle. Not the formalism is not necessarily required here for you. It will be required if you go to the math or you take the math course. But what you need to understand is why the GCD moves around, because any factor of A and B will have to be a factor of R, and any factor of B and R, by the nature of linearity, will have to be a factor of A. They can't have different GCDs. It's not possible for A and B to have a common factor of 17 without R having that 17 also. It's not possible for B and R to have a factor of 11 without A having that factor too. Because linearity causes the multiples to remain a multiple. So this is a formal proof of why that is. That's what we needed to do to get to the GCD. So now, the stuff that we started at recitation to play with was this idea that additive inverses are very easy. We can call this theorem 5 in here, to keep a track of them, 4, 5. We have this multiplicative inverse. A minus 1 mod m sometimes exists. That's something you need to keep in mind, that the multiplicative inverse is not a done deal. It's not a guaranteed thing. The additive inverse, it's a done deal. You can always add something to get to 0 or subtract something to get to 0. But you cannot always multiply with something to get to 1. So the definition here is A at minus 1, that's the inverse. When you multiply with A, you get 1 modulo m. If it exists, it's unique. So it's guaranteed that there's not more than one of them. So if you find it, say by guessing, I guess the inverse, that's it, because I can verify it, I'm done. So for example, if A is 5 and N is 26, we said, what's the inverse? Remember this problem? I think it was 21, right? A at minus 1 got to be 21, because 21 times 5 is 105, which is 26 times 4 plus 1. So the 26 is the n, 4 is the quotient, 1 is the remainder. So that is 1 modulo 26. Simply because I multiply the 21 with the 5, and I get 1 remainder, I know for sure that's the inverse. How did I find it? I just guessed it. No, I knew it from last week at recitation, but my point is, if you can guess the inverse, it's easy to check. Sometimes guessing is not that easy though. It's not immediately easy to say, okay, 5 inverse is 21, modulo 26 or some other number. So if you get a problem with the inverse, if you could guess it right away, great, but if you don't try to guess it, because that could be a slow process. Instead, we said, here's a method to find that inverse more systematically. We say build a set of powers. We did this at recitation. And all of them, up to they repeat, all of them is modulo n, in this case 26. For a equal 5, that would be 5, 5 square. 5 square is 25, modulo 26. That's minus 1, right? And then 5 cube is, if this is minus 1, multiply with another 5, I get negative 5, which if I flip on the other side, modulo 26 is 21. And then 5 fourth is, I can say it's 5 squared, everything squared. That's 1. I know that's all the set. From here on, they're going to start repeating. Once I see the 1, if I multiply with another 5, what am I going to see? 5. And if I apply another 5, I'm going to see 5, let's say like 5 squared. So if I keep multiplying with 5 in here, I'm going to have these values repeated. Right? Exactly the values 5, 25, 21, and 1. This is the only values I'm going to see, and they're going to keep repeating. Right? Because clearly, all of you can see, once I get 1, when I multiply with 5, I'm back at 5, and then I multiply another 5, it's going to be 25. Another 5 is going to be 21. 1. I can multiply with any number of 5s I want. It's always going to be in this small group here, or set, right? My point is, if this happens, along the way, we must have seen the inverse. When this happens here, we call this V the order. That is when 5 at V, or A in general, A at V equal 1 modulo n. That's the order. And what we did past week was to say V at minus 1 must have been the inverse. That is A at minus 1. So if you ever see a 1, the previous power was the inverse. There's a very simple explanation for that, right? Why is the previous power the inverse? According to the definition of inverses. Louder. So why is the previous power not the one that gives me 1, in this case 4, but 3? This is the inverse, 5 to the 3. Yes?
When you multiply by 5, it will give you 1.
Right, because this one clearly multiplied with another 5 gave me 1. That's the definition of the inverse, and I know it's only one inverse, so it's got to be that one. Hands up, who is with me so far? This is the same thing we did at recitation. We're playing with those powers. V was the power that gives me 1. V minus 1 gives me the inverse. Now, this doesn't happen all the time. We look at some example at recitations for which what happens, you build this power set, you don't get 1, right? That can happen. If I don't get 1, they start repeating, just not with 1 in there, then what? If I see those powers repeating without the 1, what can I say? There's no inverse, right? So if 1, I'm going to have a theorem here. Theorem number 6. That's actually a critical theorem. Let's put a bunch of stars to it. You know, like you have in the recitations, few stars? This is the theorem that the whole cryptography number theory stays on. What does it take to have an inverse? These following statements are equivalent. There is an inverse, aka A times A at minus 1 is 1 modulo n. The next statement is GCD of A and n is 1. To have an inverse, it's necessary and sufficient that there is no common primes between A and n. In other words, if there is no common primes, let's read this in English, no common primes. Like in here, 5 and 26, do they have any common primes? No. That's why there is an inverse. And it works the other way. If they have common primes, there is no inverse. And the other statement is 1 does not belong to that power set, P of A. If you build this A squared, A cubed, so on and so forth, you don't see a 1 in there. Which is what we've done past week at recitation, right? We say you build this set and you don't see a 1, you can declare no inverse. This is a theorem, I think is the last theorem that you have in the number theory part 1, aka the required notes. So we're going to need to prove this theorem. The remaining part of number theory, which we're going to do on Sunday, it's not required, that's optional. So, how do we prove this? Some things that are easy in here. Those three statements are equivalent. I'm going to work some of that, and I'm going to leave some of it for you to deal with at home. If you can't figure it out, you can read the notes. If you still cannot figure it out, we can take over it again. One part that's very easy is to say, I'm going to prove the first thing. If there is an inverse, aka A times A minus 1 is n cubed plus 1. That's what an inverse means. When I do the division with n of the product, I get the remainder 1. Then, the GCD of n must be 1. There can't be any common factors between a and n. That's extremely easy to prove. So I'll do that in class because I like easy things. Right? Say by contradiction or whatever. Let's say there is a prime that divides, say the GCD is not 1. So there is a prime number that divides both A and divides N. That's what it means to have not one GCD, means there is some common prime factor. Well, I look at this equation and I say, I'm going to read that A times A at minus 1 minus N cubed is equal 1. Now, if P divides this and P divides this, I apply the same mechanism that I've done before. If P as a prime factor divides this product and this product, it divides their difference. So P must divide 1. That's a contradiction. Done. That's the easy part. It says, if you have such an equation, that's the same like we did for Euclid. Such an equation is a linear equation between this part, and this part. Any factor that it's in A and N will have to be a factor of 1 because 1 is their difference. And that's not possible, right? 1 doesn't have any proper factors. Therefore, there could be no factor between A and N. Hands up who's with me here. Do you have any questions about this? That's the easy part. The hard part is, what if the GCD is 1? Then I want to show there is an inverse. Problem with this kind of question, that the conclusion is there is something or exists something, is that it's often easy to prove something exists when you can put your hands on it constructively. Find me the inverse. Now, mathematics, to prove existence, maybe you just do it philosophical. There's gotta be one, but I don't know what it is, sort of thing. That's much harder, right? Because it's an object that we don't have. It's hard to prove its existence if we can point out, here it is, right? The easiest way to show this guy was present in my lecture was to show a picture with him sitting here watching me, right? That's an easy way to show that he was here. But if I prove it existentially, like where else could he have been? You know, check his phone. That's much harder than to show a picture with him in the chair, right? Same thing in here. If we could put our hands on that A at -1, it's easy to show it exists. There it is. So how do we do this? We're going to use that power set, right? We want to prove existence, so I'm going to say, let's look at PA. That is A squared, A cubed, all the powers, all of them modulo n. So I'm not doing the actual exponentiation, I'm just taking modulos. Now, we made this point at recitation already. PA is finite because it's modulo 26. Sorry, not 26, modulo n. Modulo n, there's only n values that you can have. So no matter how many powers you list in here, the actual values are only n values. So what that means is I build these powers. At some point I have to see the same value. So that means values repeat. That means I can get an A at some power, K, that's equal with A at a different power, K plus V, modulo n. V in here is not 0. That's what it means to repeat, right? It means modulo n, when you look at some power here and some other power, you get the same reminder. So what does this mean then? Is everybody on the same page with me here? K is just some power. I don't know what power is. Maybe K is 1, 2, 3, 4. V is just some other power, not 0, because 0 means K equal A to the K equal A to the K. That's not what I mean. I mean different powers. Like for example, 12 and 17, right? So when I say exist two different powers, one of them is K, one of them is K plus something, a bigger power than that. So far I said values must repeat. Let's take two powers that have the same reminder, but not the same exact power. So this thing here means, if I do a common factor, AK plus V minus AK equals 0, more than, just moving one on the other side. If I do a common factor here, I get AK times A to the V minus 1 equals 0, more than, right? But what does it mean? I want to get rid of the modulo. That means AK times A at V minus 1 is n cubed. Because modulo 0 is a multiple of n. That's what it means. So I'm not in modulo mode anymore. That means n divides AK times A at V minus 1. Because, right? Now, I have another thing in my head that says, now I'm going to use I'm going to start using the premise here. If n, the GCD of n and A is 1, no common primes, that must be the same between n and any power of A. It's 1. Do you feel I'm trying to cheat you here? Or is that an obvious statement? If there is no primes common between n and A, there is no primes common between n and any power of A, because all the primes that appear in the power of A, where are they coming from? They're coming from A. They, of course, are different powers. If you look at this, factorization, when I raise A at a power, what am I going to get in the factorization? The primes are the same. The primes are the ones from A. It's P1 times P2 times Pk. That's the wrong K. Let's lift the power. M. What's going to be the exponent here?
2 EGX.
Hmm?
2 EN.
2. So the exponent was E1. I raise at the power m. What exponent am I going to get here? ME1. How about here? ME2 up to MEK. Right? All the primes that were there now I'd raise at whatever power I raised the A. So back to my point here. If there were no prime in common, there would be no prime once I raise A at some power. And now I'm really going to cheat you, okay? Because I skip a theorem. Let's see who can prove that. I have this n divides a product. And I say it has no primes with AK. And I'm going to conclude if that's the truth, then n must divide the other thing. Let me write this nicely so you can see it. A at v minus 1. From these things, I say n must divide A at v minus 1. In other words, n divides the product of two things, but it has no common primes with one of the factors. Then it must be dividing the other stuff. Now, what happened here, we did this theorem, but not for a general n. We did it for a prime. Right? Where was it? Was it around here? Right, we said if a prime divides A times B, it has to divide one of them. That's a variation of this theorem that says, well, this is not a prime, n. It can be any number. But it's prime with one of the factors. Then it has to divide the other one. Do you believe me? Please? No. Do you, don't believe me if you feel like not believing me. So let's take a moment and rewrite this theorem here. What just happened here? That's a theorem 5 prime. So the theorem that we needed was to say if n divides a product, A times B, and the GCD with one of them is 1, then n must divide B. Can anybody prove this by the end of the lecture so I don't have to? Okay, by Tuesday. But more important than the proof is the intuition. Do you think this is true? What's the intuition here? I think we need to go back to the prime factorization, yes?
So if n divides A and B, all the primes in n have to be in A and B.
Right, all the primes that are in n have to be in the product, but
none of them came from A.
but none of them came from A, so all of them must come from B. It's the same mechanics that we had in the other proof with the prime, right? If n divides a product, that's in principle, this is a critical condition, right? I mean, without this condition, that's not true. It's not true in general that when n divides a product, it has to divide one of the factors. But if it has no primes with one of them, then it has to completely divide the other one. So here's the deal. Try to make this proof. It's in the notes, and if you struggle with it, we'll get back. Often in the final exam, we have one problem that's related to one of these proofs. So I would strongly suggest you get familiar with them. They're all very simple proofs. Not this one here, and not the Euclid, but the other ones. They all rely on just look at the factorization and get the intuition of where those factors are coming from. The actual proof is just, I factorize n into factors. Where are those factors from? They're not from A, therefore they must be from B. So now you believe me here? If n is prime with this one, that we already know, then it has to divide the other one. So, what does that mean? I think that means AV is 1 modulo n. If AV minus 1 is a multiple of n, A at V minus 1, that means A at V must have the remainder 1 when I divide with n, right? I mean, that's what the definition is. That's to say, I'm saying AV minus 1 is n times k, not k, something else. N times p. And then that means AV is np plus 1, which is AV is 1 modulo n. Yes?
Going back to that previous step, The reason that works is because n is relatively prime with AK.
Right, relatively prime is just another way to say GCD is 1.
Okay.
So GCD 1, maybe we should say this. This in here, this statement, some people say relatively prime. That's what it means. They have no common factors. It doesn't mean A or N are actually prime. That's not it. For example, 20 and 9, are they relatively prime? Are any one of them actual prime numbers? No. But they relatively prime means their GCD is 1. Other people call this differently. Other people call it coprime. Take your pick for what you want to call them. Coprime, relatively prime, GCD equal 1, no factors mean the same exact thing. So my point in here is that I'm done. Because I found the inverse. Where is the inverse? If A at V, some power V is 1, who's the inverse?
A at V minus 1.
A at V minus 1. And I also proved along the way this part. I said if there is a GCD, 1 must be in the power set because I found a power that gives me 1. This is a proof that I would like to require you to understand it, but I can't because if it's not in the exam and the homeworks, you can just ignore me. So I think this is a useful thing to know how to do as a mathematician, but clearly this won't be in your exams and homeworks. This kind of proof. The other ones, the simple one with factorizations, very likely there'll be a problem related to that. So you are forced to look at the factorization of A, B, or N or something like that. But this and the Euclid are not in the homeworks and the exams. But this is the fundamental theorem that characterizes the multiplicative inverse. You want an inverse, you have to have relatively prime numbers. And that the same thing as saying when you build that power set of A powers, you're going to see 1 in there. Well, I said it wrong, right? It's got to be in there. So when there is an inverse, GCD is 1, and 1 is in the power set. Or the other way, if there is no inverse, GCD is not 1, and 1 is not one of the powers of X. So that concludes this set of number theory notes. The one thing I want to start now and continue on Sunday is to give you a hint at this extended Euclid algorithm, which is just like the Euclid with one more thing. So I'm going to take an example that we already did. We want the GCD, I'm going to say extended Euclid, GCD of PS1, 51, and 9. The way we did it, we say A is 51, B is 9, Q, remember, and R. And so what is it? What was the quotient and the remainder? 5,
and 6.
6, and then the next A is 9, the next B is 6, the next Q is 1, 3, and then I get 6, 3, 2, 0. 0 is my stopping condition, and the GCD is this 3 right here. Last B is the GCD. Everybody knows that, I hope so, because guaranteed one of the questions in the quiz is going to be, do the GCD Euclid for 2 values. What I want to add to this table is those magic coefficients x and y, and I actually want to verify ax plus by must be the GCD. So the x and y goes exactly like the Euclid. We can't compute x and y here. It's almost impossible. But we have to wait to go down to the last line and then go back up with the coefficients. my point is, on the last line, it's easy to see I need 6, right, times x plus b is 3, right? 3 times y, I need that to be the GCD is 3. So what would be the x and y that would work here? Yes?
0 and 1.
0 and 1. That's always the case at the end, because at the end, this is the GCD. If I give this one the coefficient 1 and the other one coefficient 0, I'm going to get the GCD. So at the last line in this table, it's always 0 and 1. Now, how do I go back from here to the previous line? In the previous line, what do I need? 9 times something, that's a different coefficient, plus 6 times something equal, the GCD is the same, right? GCD doesn't change, it's all 3, has always been 3, all these pairs. That was the Euclid theorem, the GCD is the same. So how do I want some sort of procedure that says if you know the coefficients here, you can somehow magically get the coefficient there, right? How do I do that?
I have a question. Do x and y have to be integers?
Yes.
Okay. Positive integers or?
No, any integers. Yes.
So you could do 1 and negative 1?
Correct. I can do 1 and negative 1, right? But you guessed it, right? How did you produce 1 and minus 1? He looked at 9 and 6 and said, I know how to get the 3 out of here.
Yes.
Right. I'm saying it would be nicer to have some sort of procedure, something like I can implement in a computer that says, if you know the previous coefficients, 0, 1, there is a way to get the coefficients above. Yes?
Does your y become into x?
Right, so here's a speculation. This y here, no, you say what, y, this y becomes this x?
Yeah.
So your speculation is x new, this guy, is the y old. Is it right? Is that just going to work out that way? And how about this one? How about the y new? What is this? How did I get that minus 1?
The old x minus 1.
What?
The old x minus 1.
I don't know. It's in this note somewhere. Right? No, there's a monster formula that nobody can remember. Right? There is a procedure that says, related to the fact that there's a relationship between the pair 9, 6 and 6, 3. The relationship is the integer division, right? There's a way to get from these coefficients to these coefficients, a fixed formula. In fact, I have it here. Let's see. It says, indeed, this is correct. And this is x old minus q times y old. Is that true? So how much is x old? 1, right? Or 0? 0 minus q on this line is 1, right? Times y old is 1. So that will be minus 1. So I think these are the formulas that we need. Let's try to move from this line to the first line. So this thing is coming here. How about in here? Here we need 51 times something plus b in here is 9 times something equal 3. If I apply these formulas again, y has to move in here, right? That would be the point. The new x is the old y, so let's just move that one here, minus 1. And if I apply this formula for the y, what would I get? X old in here is 1
Minus negative.
minus the q 5 times the x old.
That's negative 1.
How much?
Negative 1.
How much is that? 6 work? Who does?
Yes. 54 minus.
Oh, yeah, yeah,
To
yeah.
154.
It's in the notes, so it must be correct, right? I don't think anybody can reasonably remember these two formulas, honestly. Maybe the first one, x nu is y old. I don't know anybody who can remember this one here. But the way people figure it out is because they know the equation, A is BQ plus R. So they figure it out from the equation when they need it. Of course, when you implement in a computer program, you just implement it once, you verify it, and then it stays in there in the program. You don't have to worry about it. But we agree that there is a very easy way, computationally speaking, O of 1, constant, to get from the old coefficients to the new coefficients? This allows me to get the original coefficients by first doing the GCD all the way down to the last line, get the GCD, and then the coefficients go back up. So the algorithm went down up to the GCD, but the coefficients computation went up. This equation, ax plus by equal the GCD, is another big deal in number theory. Because this also gives me, so there's several very important things about this. First of all, once I have this, I can say what is the set. If you are to consider all the x and possible y's, and you look at the set of ax plus by, all the linear combinations with all kinds of integers, you're going to get, that's just all the multiples of the GCD. So this set here, when you start plugging x and y's for two numbers a, b, and you get all the possibilities, is the same set as all the multiples of GCD. For example, let's say a equal 15, b equal 25. What is the GCD? 5. What this is saying here, if you build all the possibilities of 15 times x plus 25 times y, with all the possible x and y integers, for all integers x and y, what set is that going to be? That's the set of the multiples of 5. So that's going to be 0, 5, minus 5, 10, minus 10. That's all the numbers that are 5k. So by creating linear combinations of two numbers, what we effectively create is all the multiples of the GCD and nothing else. That's one important fact. That's how a lot of fancy number theory theorems are proven. The other important fact is a particular case when the GCD is 1. If the GCD between A and B is 1, which is our big case in here, when there is an inverse, they're relatively prime. What is this theorem saying? Find some coefficients that have what property? Ax plus b1 equal 1. That's not a modulo statement. That's just integer statement. Right? This is not a modulo equation. This is saying there are two coefficients that when you plug them in, you get exactly the GCD. So by the way, for 15 and 25, what are the coefficients? 15 times what plus 25 times what give me the GCD, which is 5. How do I get the 5 in here?
15 times 2 is 25.
15 what?
Minus 1. 15 times 2
Times 2 plus 25 times?
negative 1.
Minus 1. So it's very useful to think of the GCD as the value I can obtain with some coefficients. In the case of 1, this becomes more interesting. If I could get 1, the integer 1, then I know who's the inverse of A, modulo B. Who's that?
AB minus 1.
The inverse, the multiplicative inverse. Who in here multiply with A gives me the remainder 1 modulo B? Who? X. And by the way, I also know who's the inverse of B modulo A. Who's that? That's going to be y. You just look at it. Y times B has to be 1 plus a multiple of A. That means the remainder is 1. So why is this so important? Because this is a very efficient way to find the inverse. These x and y are exactly the inverses of A modulo B and B modulo A. So I don't have to do that power set. And has an additional advantage that this algorithm, before it gets to x and y, it computes the GCD. So just by looking at the GCD, I can decide what? What? If there is an inverse or not. So I do the GCD, I get here. If I see 1, I go compute the coefficients, x and y, and the coefficients are going to be exactly the two inverses that I want. So let's write that down. Extended Euclid to find A at 1 1 modulo B. First thing, do the Euclid GCD. And then if GCD is not 1, you can stop. You say no inverse. We already know if the GCD is not 1, there will be no inverse. Now if the GCD is 1, continue to calculate x and y with the property ax plus by is the GCD, which is 1. And then when that's done, we have x is the inverse we're looking for. This is the actual method that's being used in cryptography. When I want to find an inverse of a very, very large number, modulo another even bigger large number, that's the method that's being used. In large numbers, we have to implement those methods in a logarithmic time. The numbers are so big that anything algorithm, multiplicative, exponentiation, GCD, whatever, that doesn't run in logarithmic time is just too expensive. So there's a computer science question. How do you make this algorithm run in logarithmic time? Is size of A and B.
Oh, I was just about asking what time does that algorithm runs.
Right, so Euclid and extended Euclid have to be able to run in logarithmic time to be useful for large numbers. In cryptography, the numbers have 2,000 digits. So the magnitude of a number is 2 to the 2,000. Anything that runs linear in that size is too slow. But what logarithmic runs means is the number is 2 to the 2,000, it has 2,000 digits or bits. Then it only takes 2,000 steps in a logarithmic algorithm to perform whatever computation I need to perform. For example, the GCD, that's acceptable. Question?
Yeah, I can't read what that said. If GCD equals 1, then what?
Here?
Like that's if
Right.
GCD equals 1.
Here.
Yeah.
So the equation says ax plus by is the GCD, right? Which is 1, because I'm in the case when the GCD is 1. If the GCD is not 1, I don't have to do anything, because I don't need to find any, I know there is no inverse. Hands up again. Who's with me so far? How many people we lost along the way? Okay. Euclid extended is not required for the exams and the quizzes. But Euclid not extended, this part, find the GCD, that's required. So you're going to get a question guaranteed that says, here's the number, find the GCD. You may also get the question, find me the inverse. So for those of you who studied this, you can find the inverse this way. What's the other way to find the inverse? Power set until you get 1, right? And what's the other way to find the inverse? Guess it. I wouldn't rely on that. But if you guess it and you verify it, that's good. Full credit. Okay. That's what we needed to do to finish the number theory. And then we're going to have Sunday the other lecture that is RSA, we're gonna start exactly from here, from GCD Euclid Extended. From here, how do we go further into how RSA Cryptosystem works? Because we're quite far away from cryptography right now, but that's enough for what we need to do for the class. So, in the remaining half hour, I want to talk a little bit about something we've already done, but just to recap it. These graph algorithms that come, and you may have 4 more questions about them, are not the theoretical analysis algorithm that you're going to see in your algorithms course. I think it's 4800. So you only need for now to understand the intuition of that is, which is quite easy. You're not going to be required to do proofs on that. So I'm going to move into graphs and graph traversal. I think we already talked about those. So very soon I'm going to connect my projector here to show you a demo. But here's the idea. If I have a graph, what kind of graph is this? Is directed or undirected? That's directed, right? A goes to F this way, and E goes to F that way. Think I've got all the edges here? No. B goes to E. All right. So this is directed graph. In a directed graph, edge UV is not the same as edge VU. If you really want both edges, you have to put both edges. Because if you can go that way, it doesn't mean you can go backwards. But you can have both edges. And correspondingly, in the adjacency matrix, it's not symmetric. If I see a 1 from S to A, it's not necessary that I have a 1 from A to S because that edge is not there. Only in undirected graphs, edges work both ways. So then that matrix, the adjacency matrix, will be symmetric. So what we want to do here is do 2 things. One is the Dfs Depth-First Search. Some people find it easier to remember by the data structure they need to control the algorithm. How many people know what a stack is in computer science? How many people want to know what a stack means in English? The word stack in English. Hands up. All right. So just in case you didn't raise the hand, both questions is the same thing. Okay. And the other one we're going to do is Bfs Breadth-First Search. Some people find it easier to remember by using Q. You don't have to remember the stacks in Q, just might be easier. Let's start in S here and see if I use a stack. The idea is once I go depth first, once I go to a node, like A, I'm going to choose A to go. And always the idea of a traversal of a graph or exploration of a graph. Add here exploration. Is I move from S to some unseen node, something I haven't seen before, say A. The difference into Bfs and Dfs is in Dfs I continue exploring from A. In Bfs, I'm going to go immediately after I went to A. Where else can I go? I can go to B. So let's write that first step. We start in S. And in DFS, the next thing in the stack, or the next thing I'm exploring, it's going to be, this is the stack, goes up, because it's a stack. And the next thing is going to be A. In BFS, I start with S, that's the starting point. It's a Q. So the next thing could be A. That's, say, in both ways I can go to A first. Usually when I have multiple possibilities, I choose one of them. Now what's going to happen in the stack after A? Who goes first? Who goes next? Once I got to A and I do DFS, what do? I go to E, right? Because from A, I'm asking where else can I go from here? I don't go back to S. I go to E. How about in BFS? In BFS, what do? I visited A, but in BFS, the principle is don't advance from A until you finished L advances from S first. So who's next?
B.
B. In BFS, it makes sense to chop it off, to say that's like a wave 1, that's level 1. Because that's the one that I can reach immediately from the source. Right? A and B. Well, in here, once I'm in E, what do I do from E? I can go to, for example, F, right? So I could mark these these arrows that I took in here. So it's this one, I took this one, right? I'm going to do E, and from E I could do F, and then from F, what else? From F, I see this arrow, but this arrow points to something I've already seen. In DFS and BFS, I must keep track of what I've seen already, otherwise it becomes a gigantic mess. Right? So it's absolutely required that I have a lookup table that says exactly for each node what status it has. Status that could be, I've never seen this before, I've seen it, or I've seen it and I'm done with it. A bunch of status options in there. In here, once I've seen it, I say, I'm not going to need this edge. It's an edge that points back to something I've seen. I don't need it. So what else can I do from F? I cannot do anything, right? So I go back to E. Can I do anything else from E? What can I do? I can go to G, right? So what edge I've been using? I've been using this edge here, G. And from G, can I do anything? I can go to D. From D, can I do anything?
C.
I can go to C. So I've been using this edge, right? And from C, can I do anything?
B.
B, using this edge. From B, can I do anything useful? No, these edges are not interesting because I don't need them. They point out back to things that I've seen. So I go back to C, I go back to D. Can I do anything useful from D? Can I? Do this, right? So the traversal order, the order in which I visited those vertices is going to be A, E, F, then what? Back to E, right? Because in F, I'm done. It's not F that goes to G. This is after F, I go back to maybe the right way to put that in. Let's see if we can write it like a stack. F, from F, I need to go back to E. Then from G, I go to D. From D, I go to C. From C, I go to B. Now B, nowhere to go, goes back to C. C, nowhere to go, goes back to D. And from D, I can also go to H, right? So the stack can go up and down.
Is the lookup table keeping track of the edges or the nodes?
We keep track on both edges and nodes, but in different structures. The nodes we keep track of visited, not visited, or some intermediary state. You'll see when you study DFS, there's black nodes, white nodes, and gray nodes. White means unexplored, black means totally done, and gray, still I'm exploring from there. We also need to keep track of the edges. The most important edges are the ones that allow the advance, the bold ones. The edges that allow me to advance to a new vertex. When you do DFS at the master level, that is in 5800, of course, there's more interesting edges here. Of course, you have the advancement edges, the ones in bold, but the other edges have multiple flavors. Some of them can go back to something you've seen. Some of them can go cross to something you're already exploring from. So you'll see that the cut edges are actually multiple classifications, but you don't need that for now. The most important edges in DFS and BFS are the edges that allows you to move to new nodes. Those in bold are the ones that allow me to explore another node. How about in BFS? I done A and B, so I've got kind of these guys done. I'm going to make level 1. That's what I could do first. From A and B now, where can I go directly?
Theory.
I can go to just E,
And B.
B2. So for BFS, this edge, I have to pick which edge I choose to go to E, right? I could go from A or from B. That's up to me. But this edge must be used to advance to B, right? So this is a BFS edge. And say this is a BFS edge. Now I've got E and D, so this is like level 2, right? So from E and D, where else can I go?
Factorial.
I can go to F, G,
M and C.
H, and C, or not? F, G, H, and C. And that's done. So this is level 3. The right structure to control the BFS mechanism is called a queue. Whatever comes in is processed first, and then as things go in, that's the order they get. The queue is first in, first out, so to say. If you don't know those, no worries, because we're not going to implement BFS right now. But to implement BFS, you need a queue. In DFS, unless you do it recursively, what you want is a stack, which is last in, first out. The last element that I've seen is the one I'm exploring from. And I won't go to the previous one until I finish exploration from there. That's why we ended up going all over the graph before we even use this edge, right? Just from A, we explored everything, so we didn't need this edge. So DFS keeps going, advancing in as aggressively as it can. While BFS says, no, just get the close neighbors first. Once you got the close neighbors, get the next set of close neighbors, and so on and so forth. Those are without proof. Both of them have runtime. V plus E. This is the number of vertices. This is the number of edges. It's easy to see why they must be at least V plus E. You need to process the edges and the vertices, because otherwise you can't process the graph. And if you pay attention to how they work, they only process edges at most once. So every edge is looked up once, and every vertex looked up once. Therefore, you get this running time. This is really O of E in most graphs, because most graphs have more edges than vertices. But there are those very sparse graphs, very disconnected graphs, in which I have almost no edge. So I have to look at all the vertices. So V plus E is really more like, the way you should read this is maximum between E and V. Usually it's E, because most reasonable graphs have at least that many edges. So what I want to do is to show you something on my computer. Here. I need to shut down some lights. Let's see if this works. All right. Just some slides I have for my algorithms course. We can skip some of this stuff. The ones of you who want to read them, those are perfectly readable. It's not nothing fancy in here that cannot be read. But you don't have to do everything in here. So some stuff of the graphs that we already done, adjacency matrices and lists and all that, cycles, edges. This is the traversal BFS. I think this might be the same graph, maybe not, I'm not sure. I think we're missing an edge here.
Yeah.
But the idea of BFS is extremely intuitive. The wave one is just where you start, 0. Then what can you get in one edge from there? So the Q contains just S in the beginning. From S I go to A and B. So now I have A and B in the Q. Where can I go from A and B? I can go to D and E immediately. So now my Q has D and E. And then where else can I go from D and E? I can go everywhere now. What BFS could be applied for, very commonly, is the idea of shortest path in the sense of number of edges. Say in Facebook, how many friends do I have to jump through to get from me to him? That's typically a BFS problem. You start from the source and say, what are your level 1 friends? That's the friends that I'm friends with, direct edge, right? From these guys, the level 1, who's level 2? Well, those would be all the friends of my friends that I don't have a direct connection with. Because if I have direct connection, they will be in level 1. Does everybody see that? So level 1 is my immediate friends. Level 2 is their immediate friends that are not mine, and so on and so forth. So if I count those levels, say at level 5, I get to some person of interest, it means the shortest path to that person through Facebook friends, it's 5. Why it's 5 and not 4 or 3? So in other words, why BFS reaches G at level 3, I know for sure is not reachable in less than 3 edges.
If you could reach it in fewer than 3 edges, then it would be in a previous way.
Right, if it be reachable in 2 edges, it will be in level 2. If there is a path of 2 edges that go to G, then BFS will find that path and will say G must be in level 2. Same thing, if there will be a path of friends, Facebook friends of only 3 friends, by the time I get level 1, level 2, level 3, the person of interest will be included in level 3, so the path will be 3. So a typical application for BFS is what's the shortest, not quantitatively, but shortest by number of edges path to get from a source to a destination. Yes?
Is your runtime based on the total amount of edges inside the graph, or the amount of edges that you have to traverse, or the vertices you have to traverse?
Total amount of edges.
Okay.
It might be an O there, like an upper bound. Let's say O. In certain graphs, you can probably do it faster by taking advantage of the graph. Certainly not more than O, V plus C, which is considered for most graphs a good time. Now, if you're Facebook, you probably need to do something faster than this, because the number of edges and vertices is gigantic. But for most graphs, O, V plus C is considered a good running time. Just processing every edge once, it's O, V plus C, right? So BFS, the other application of BFS is connectivity, and the other application of BFS is coloring. If you remember very early on, we talked about bipartite graphs, for example. Bipartite graphs had the left side and the right side, and all the connections, all the edges were going from one place to another. Later on, we talk about coloring, or red and blue. BFS can deal with coloring. It says, I'm coloring the first level red, the next level blue, the next level red. If that works out without errors, the graph must have been bipartite, because every time I move an edge is from red to blue, and every time I move in the edge from blue to red. So coloring BFS levels is equivalent to look at bipartite graphs coloring. Like whether a graph is bipartite or not has to do with whether BFS can color those levels consistently.
That same algorithm would work in a depth-first search though, right? If you colored as you went.
Right, the problem is in DFS, maybe you can do it just, if you go, you don't see all the neighbors, right? At some point you gotta ask yourself, do I have a contradiction of colors at what level that was, right? In BFS I know for sure I already colored level 1, level 2, level 3. I'm not sure how to answer your question. In DFS, when you come to a node, you have to make a judgment of what color you're putting there and what level that node is.
So it would work for coloring, but you wouldn't notice if it wasn't actually bipartite in the first place.
I think you can make it work.
Okay.
Coloring has to do with simple coloring, 2 colors, bipartite, has to do with if I assign a color for, like, I'm certain it has to be red. If later on I want to assign blue, I know I got a contradiction. Okay, here's a little bit of pseudocode for BFS. If you're curious, you can take on a programming language and implement this to see how it goes. Here's DFS. Here's a different example in DFS. Like I said, we have to keep track of the status of the vertices. Initially, all the vertices are white because they're unexplored. I start in A. I color A in gray, which means I'm exploring from A, I'm not done. Black would be, I'm done with that node. So I start from A, I go to D, I mark the time in DFS, at what time I've seen that. That's 2. From there I go to 3 right away. And I'm listing there what happened in DFS. From 3, what happens in here? Can I go anywhere else? No. So I close this node, I make it black, there's nothing I can do from here. And now I go where?
Back to D.
I back to D. Can I do something from D? Yeah, I can discover F. So I'm measuring the time. Can I do anything from F? No, so I close this. Then where am I going to go? Back to D and close it because there's nothing I can do in D. And now I go back to A, but I can do something from A. I can go to B, right? And from B, can I go anywhere?
G.
To G. From G,
No.
I close, which means I now close B, and now I close A. That DFS run is done. It's everything I can find from A. The C and H are not discoverable from A because the graph is directed, I can't get there. So I need to say, if there are vertices still unexplored, which I know because they're white, right? I can start another DFS run, keep track of the time. Since I closed at time 12, I'm now moving on time 13. And I say, okay, 13, 14, close, close, now I'm done. I may have to do multiple runs because when I start somewhere, it's not guaranteed I'm going to reach all the nodes in the graph. If I'm reaching all of them, it's done in one run. If not, I have to keep going from the nodes that are still white. Hands up, who's with me here? DFS, extremely useful for finding cycles and graph patterns. DFS edges have a categorization. The most important edges are the ones allow me to advance, but like I said, if you study DFS for real, it matters the other edges that you didn't use to advance, what kind of category are they in. Depending on these edges, you can get to understand the structure of the graph. Every edge can cause a cycle or a DAG, what's called a directed acyclic graph, or some other pattern. In DFS, it's also very useful to keep track of these times because by looking at the times, you can reconstruct back the DFS run. Just if I tell you the times, you know how the DFS went. The last observation I want to make here is that these edges that we use in DFS, the black one, the bold ones, form a tree. That's easy to see. I keep advancing. I'm never going to get a cycle because no edge will be used to go back to the nodes that I've explored. So this you might see the notion DFS tree. That is the edges that DFS used to advance to new nodes, form a tree. I have some other stuff in here that you don't have to do, but might be useful to check. For example, how to find spanning trees. Spanning trees are trees that are connecting the graph with v minus 1 edges, like we know, right? The question that I'm looking for is if I have undirected but weighted graphs with the weights on the edges. So that's in problems where I have a pipe distribution system and different pipes have different sizes or bandwidth routers and the capacity of the network is given to me. How do I find the minimum spanning tree? I'm pretty sure we did this already. We talked about this. So in here, I'm not asking you to remember this algorithm, but I'm requiring you to remember what a minimum spanning tree is. It's the spanning tree that is guaranteed to have v minus 1 edges that has the minimum total weight. And here's some algorithms of how to find those. I use that edge. I use this. So the principle of a spanning tree to find the minimum is if I have some edges already on, you see these ones that are colored in gray, the question is what edge can I add to this to keep going with minimum spanning tree? And in this algorithm, we're always adding the edge that still connects to that tree, but is the minimum possible. Of course, we want the minimum weight, because the minimum weight is what's going to cause the minimum total weight overall. You don't have to know these algorithms, but you have to know what's a minimum spanning tree. You might get the problem with the graph. Here's a spanning tree. I might ask you, is this the minimum spanning tree? And if you find a different spanning tree, different set of edges that cause a tree with a less weight than the one given, then it means you found a better spanning tree. So that's that. Next time we can spend a little bit more time about graphs. The reason I'm not insisting on graphs is because my belief is it doesn't make much sense to study graphs without actually implementing them. So like I think the right way in here is, if you want to study it properly, which you probably don't have time to do right now, is to actually spend time with these algorithms and implement them and try them on actual graphs. Because you can study those slides and you can answer the question in the homework, but you probably by Christmas will forget about this anyway. So let me show you one more thing, which I'm sure again that we've done it already. That is, how do I find, if I have weights, how do I find the shortest path from one place to another? The most important thing to remember, which we trick people in the exams all the time with, is the minimum spanning tree is not guaranteed to have the minimum from some place to another in it. The shortest path might not be the one that goes through the minimum spanning tree. So don't get confused of these things. If I want the shortest path, it's not the minimum spanning tree. It's something else. I'm sure we've done this too. And in here, we create some estimate. We look at this edge and say, how long is it going to take to get there? Well, 10, because I have seen that edge. And every time I see a better way to go there, I update that. So for example, I see this 5, I make that a 5. That's all estimated. And later on, I look at this 5 and see, I see a 5 and a 3. Would that worth the update? Is that better than the 10 I have in there? Right, so I compare, I say, if I can go there with a 5, and from the 5 I go there with the 3, that would be an 8. 8 is better than 10, so I'm just going to write 8. Because 8 is a better estimate. It's not guaranteed to be the best, it's just better than what I had before. And then, I put that as a 14, right, because it's 5 plus 9. But later on, I may update. I see here, for example, 7, 6, right? Go back a little bit. 7 plus 6 is 13, so that will cause an update up there. 14 will be replaced by 13. Oops, I'm going the wrong way. So I moved that to 13. But later on, when I explore that edge in there, 8 to 1, that's going to get even better, right? 8 plus 1 is 9, which is better than 13. So I'm going to change that. And this algorithm has a complicated proof that in the end, it's actually not just estimating, it's giving you the correct shortest path time. We're not expecting you to know the algorithm. It's very famous. You can't avoid it, your college years. You'll have to study it. But for now, you have to remember that shortest paths work through this kind of update, and shortest path between two vertices is not the same as the spanning tree. Finally, I want to show you a movie that impresses me, because I have a present for each one of you. But the present comes with the assignment. You get the present, but you have to get back to me next week with an explanation for the present, all right? The presents are in here, so on your way out, everyone will take one of these. Let me show you the movie. What motivated me to... Remember this movie?
Yeah.
Anybody remember this movie?
Yeah.
Some people I think might have seen it. This is the first one was good. After that, it went bad. Very magic cube in there. And by the way, some people at MIT are studying exactly this problem, how to transform different forms into other forms. It's called reconfigurable robots. That's not anymore science fiction. What I have here is a bunch of cubes. We're not going to do that. These cubes can be opened in a snake sort of cubes, right? So you get to play with it. Problem is, once you open it, it's kind of tough to put it back. So what I want from you is this is yours. Pick one, it's yours to keep, okay? But I want something in return. I want a paragraph written about 6 lines on a piece of paper that says, is there only one way to put it back or multiple ways? And if there's only one way, which one is the center? And why that one must be the center? And which ones are the corners? And why those ones must be the corners? Those are the 3D geometry problems. So I want some explanation on how do I look at this and put it back. I'm not looking for the explanation that's on Wikipedia or on YouTube. I know that one already. So everybody on the way back, pick a cube. Yes?
Are we allowed to team up for this?
No. And play with the cube and tell me back.
And he gave it to me, and he said, figure of principle. It's just like, and